So today I'm going to be talking about related rates. So this is probably my favorite kind of topic to cover in calculus, or at least one of them, because it combines so many things. It combines the chain rule, which we learned earlier. It combines real world problems. It combines trigonometry for a lot of it. Just things that we've learned before, but it's implementing it into the things we've also learned in calculus and things that we see every day. For example, how fast things float, um, how quickly volumes are changing, if we're filling something with water, stuff like that. So related rates are just obviously from the name they're based on rates, but let's say we have a square, okay? Say we have a square and squares are unique because all of their side lengths are the same. They're all the same side length. So we'll just call these side lengths S. So the perimeter, right, the perimeter of a square is going to be 4S, 4 times the side length. Okay, so if we want to find out how quickly, like the rate at which the perimeter is changing, if we know the rate at which the side lengths are changing, we just have to differentiate everything on the left and right. So the derivative of the perimeter, right, the rate at which the perimeter is changing with respect to time. So typically we write that dp over dt. So the rate at which the perimeter is changing is equal to, well, what's the derivative of 4s? Well, we don't really know what s is, so we have to say 4, right? Because the derivative of like 4 times a constant is 4 times the derivative of s with respect to t. So that's the chain rule. Because remember, when we had, for example, if we had sine of 2x, and we were differentiating this with respect to x, we had to take this whole thing, the derivative of this whole thing, which would be cosine, so cosine 2x, and then we had to multiply this by the derivative of the inside. So we multiply it by 2 because the derivative of 2x with respect to x is 2, but what this really is d2x by dx. So these dx's would cancel and we'd be left with 2. But the main idea is that we have to multiply by the derivative of the inside, because with related rates, we're always using the chain rule. Okay, so what if it was, I don't know, what if it was the area of, say, a circle? Okay, the area of a circle. So the area of a circle is pi r squared. If we're trying to find the rate at which the area is changing with respect to time, so dA by dt, we would have to know the rate at which the radius is changing. Okay, so we have to use our power rule, right? Bring this 2 down, multiply it into pi, so it would be 2 pi times r, right? That looks like the circumference formula. I'll just make my pi a bit nicer here, 2 pi r. Then we have to multiply by the derivative of r, so at the rate at which the radius of the circle is changing. Because we can't just say the rate of change of the area is 2 pi r. It's only 2 pi r if this rate is equal to 1. So if the radius is increasing by 1 unit per unit time, right, that would give us a rate of change of area of 2 pi r. But it's all dependent on how fast the radius is increasing, and that's going to be the case for a lot of these problems. Okay, what if it was a volume question? Let's say we're trying to find the volume of a sphere. Okay, the volume of a sphere is 4/3 pi r cubed. And on a test and quizzes and stuff, you're going to be given these formulas. You just have to learn how to use them to solve these problems. So you're not going to have to derive these volume and area formulas. You're going to be given them. Okay? You might have to memorize a couple of them, but it's not a huge deal. So if we're trying to find the rate of change of the volume of a sphere, right, that's going to be dv by dt. That's what we're trying to solve for. Okay, and so what we have to do now is we have to differentiate the right side. So we have to figure out what our variables are. In this case, everything's constant except the r. So there's going to be a dr by dt somewhere on the right, but we have to bring down this 3. So it's going to be 3 times 4/3 pi r squared, right? Because we're reducing that exponent value by 1. and then we're going to multiply by dr by dt. Because via the chain rule, this r is technically our inside. So r is our inside, it's our variable we're differentiating, right? On the right side. The left side, we just have dv by dt, but we have all this stuff on the right we can simplify. So 3 times 4/3, that's just going to be 4 pi r squared times dr by dt. Okay, and what's kind of cool is, remember when we were finding the area of a circle, right? The area of a circle was pi r squared, and then when we differentiated this, we got like dA by dt to be 2 pi r times dr by dt, and this was the formula for the circumference of a circle. This is the formula for the surface area of a sphere. So from related rates, like, we can see how we get these formulas. We always have to tack on this dr by dt, which is kind of annoying, but it's kind of beautiful, like, when we actually differentiate them and see where we're getting all these formulas. Like, during the question, it's not even asking you to do that, but it's just kind of necessary to solve it. So I think that's super cool. Okay, so now that you kind of have an essence of what related rates are, let's kind of jump right into some word problems, because the word problems are really what make this unit like super fun. Okay, so let's go to the first question here. James is filling a basketball with air before a game. Okay, so he's got a basketball he's filling with air. At what rate is the volume of the ball increasing at the instant the ball has a diameter of 29.3 inches and the radius is increasing at a constant rate of 1 inch per minute? Okay, so now we're just really applying what we learned above into questions here. So see how it says the radius is increasing at a constant rate of 1 inch per minute? And in all the above examples I talked about, we had this dr by dt. Well, this is an example where dr by dt is 1, right? Because it's increasing at a rate of 1 inch per minute. So that's going to make our calculations a lot easier, because if we always have to multiply by dr by dt, and dr by dt is just 1, we're just multiplying by 1. So we essentially don't even need to write it, but we're going to, just to show our work. Okay, so the volume of a sphere is what we're looking at. The volume of the sphere, we just talked about it, was 4/3 pi r cubed. So at what rate is the volume of the ball increasing? So as soon as we see that, we have to think, okay, we're looking for dv by dt. So per some unit time, what's the change of volume? Okay, what's the rate of change of the volume? So we bring down this 3. Remember, the 4/3 and the 3 cancel, so we just get 4 pi r squared, and then we had to tack on this dr by dt. So if we're trying to solve for dv by dt, that must mean that we know everything on the right. So 4 is a constant, pi is a constant, r squared is not a constant, but see how they say here, at the instant the ball has a diameter of 29.3 inches? Well, remember, diameter is just 2 times the radius. So if the diameter is 29.3, we can just divide both sides by 2, right? Let me just get my calculator. 29.3 divided by 2. So we know that the radius is 14.65 inches. So this is going to be 4 pi times 14.65, okay, inches, times dr by dt, which we talked about before was just 1. So we don't even need to write that, because this times 1 is just that thing itself. So 4 pi, right, that's going to be 12.6 times 14.65. That's going to be 184.1. 184.1. And then we always need our units here. So dv by dt, remember, our unit here was inches, so this is going to be inches cubed per some unit time, because that's that dt on the bottom there. So this is going to be per minute. So units are super important with related rates, because if you get your units wrong, you get the whole question wrong. Because 184.1 cubic feet per year is different than 184.1 inches cubed per minute. So you have to keep track of what your units are the entire way. So they might throw you a harder question. They might give you a unit in meters, and then in centimeters you have to convert it. Just always be aware of what's going on with the units. Okay, Michaela is pouring bird feed into a cylindrical bird feeder 15 centimeters high, 6 centimeters in radius at a rate of 4 cubic centimeters per second. Okay, so we already know we're dealing with centimeters and we're dealing with seconds. So our dV by dt is going to be cubic centimeters per second. So at what rate does the surface of the water rise? So that's what we're trying to find. Okay, so if we know that it's a cylindrical bird feeder, okay, we know that the volume of a cylinder is going to be pi r squared, which is just the area of a circle, times h. And if you wanted proof for this, right, you might think of it intuitively, like you just see a cylinder and you think, okay, it's basically like a circle with a height. But like if you were to integrate this, like if this was your height from 0 to h, if you integrated this from 0 to h of your area of the circle, so a of x dx, this would be the integral from 0 to h of pi r squared, and I guess we could just call it dr. This would be h pi r squared minus 0 times pi r squared. So this would just be h pi r squared. So that's how you can kind of, like, if you forget how to like remember these formulas, you could always just derive the formula yourself if you know how to integrate things. But if not, you could just remember them. So the volume of a cylinder, right? We're looking for, let's see, what rate does the surface of the water rise? Okay, so the rate at which the surface water rises, let's see. So let's just write this out. If we differentiate both sides, we get dV by dt, right? And then, so now we have two variables on the right. So that means we're going to have to use the product rule on this one. So remember, we can factor out a pi. So this is going to be pi times r squared. Actually, I'm not going to write all this out. I'm just going to, we can imagine this pi is in brackets. This is our constant, multiplying it to r squared h. So if we take the derivative of r squared h, we're going to get pi on the outside, and it's going to be the derivative of r squared, right, with respect to time. So that's going to be 2r dr by dt times h, right? Because this is the product rule. We differentiate one thing, multiply it by the original other thing, and then we add the derivative of the other thing, so dh by dt times the original first thing. Okay, so this is going to be times r squared. Okay, so to simplify this, just to make it a bit nicer, 2rh dr dt, this is just the product rule, but we can't like leave out this dr dt or dh dt, plus r squared dh by dt. So this is a function of lots of things. Pi is the only constant here. So we have the radius itself, the height itself, the rate of change of the radius itself again, the rate of change of the height of the cylinder. Okay, so dV by dt, that's the rate of change, the volume, right? 4 cubic centimeters per second. Okay, that's how quickly she's filling it, so we're just going to substitute in 4 there. Pi is the same. So 2rh dr dt. dr dt is the rate of change that the radius is changing. Okay, the rate of change of the radius. Does it talk about the radius changing in this question? So see here, it says a 6 centimeter radius. So if it says the radius is 6 centimeters, that means it's always 6 centimeters. So dr by dt is 0, therefore this whole thing is 0, because these things are multiplying into each other. So we're just going to ignore this. So we just get r squared dh dt. Okay, and I'm just going to drop, I'm going to drop the brackets now, because we don't have that plus anymore, we just have times. So we're looking for the rate that the surface water rises, or the surface water rises. So that's dh dt. If we had our cylinder here, This is the surface of the water. This is the height that the water is. We're looking for how quickly this thing goes up or down. So that's going to be dH by dt. That means we must know what R is. R, right, was 6 centimeters. So this is going to be 4 equals 6 squared, right? R squared is 36, so 36 dH by dt. So therefore, dH by dt equals, we just divide both sides by 36. So we're going to get 1/9. And then our units are, well, this is dH by dt. We're talking about how fast the surface level rises. So that's going to be in centimeters per second. Okay, units are important once again. A water storage container takes the shape of a cone, which is 8 feet deep and 16 feet in diameter at the top. Okay, so I'm just going to draw this out. So this is our cone. Actually, this is our cone, which is 8 feet deep. Okay, so from here down, this is 8 feet, and 16 feet in diameter at the top. So instead of writing 16 feet in diameter, I'm going to write 8 feet in inches. Whoops. Because that's really what it is. This is also 8. So I didn't draw it to scale, but that's okay. At what rate does the water rise the instant its depth is 6 feet? So we know these are kind of the dimensions of the cone. We're saying, okay, when the water is 6 feet deep, right, how fast does the water rise? What's dH by dt, in other words? Okay, so we have to come up with an equation for volume. So the volume is going to be equal to 1/3 pi r squared h. We could derive this formula for the volume of a cone, but that's it. Okay, so the volume, what's the radius going to be here? Because on the right side, we have things in terms of r and h. So if we know that the h is 8, and we know that the r is 8 as well, right? Because we know the height is 8 feet, and we know that the radius is 8 feet. Well, we know that they're both going to be the same thing. Okay, so instead of saying r squared times h, we can just say h cubed. So the volume is just 1/3 pi h cubed, because the radius and the height, they're the exact same thing. Even though I didn't draw it to scale, the height is the same dimensions, or the same dimension as the width, or the radius, I mean. So if we differentiate everything, right, if we want to find dV by dt, I think they already gave it, but dV by dt equals 1/3 pi times 3 h squared, right? We're differentiating h squared times dH by dt. So this is going to be nice because the 1/3 and the 3 are going to cancel. So dV by dt is going to be pi h squared dH by dt. So we're looking for what rate does the water rise. So we're looking for dH dt right here. That means we must know what h is, the depth. So that's the 6 feet here. And we must know what dV is. So dV here, let me just look at what rate does water rises. Okay, so for this question, we're not actually trying to find the numerical value. All we can do is substitute in 6 for h. So the dV by dt is going to be, so the h was 6, right? So it's going to be 36 pi dH by dt. So to solve this question, all we would need to know is the rate at which the volume is increasing for this cone. So let's say dV by dt was equal to 5. Okay, or let's do a nice number. Let's do 9. Okay, what we would do is we'd sub in 9 for dV by dt, 36 pi dH by dt. So dH by dt would be 1/4 or 1/4 pi. That would be your answer. But it depends on what dV by dt is. So they were trying to trick you in this question. They didn't give you the rate of change of the volume. Okay, so there's certain things you need to know. Related rates isn't some magical thing that lets you solve anything you want. You need to know specific values. Sometimes it's going to cancel out and you don't need to know. But for this question, we had to be a bit tricky. We had to use our knowledge of similar triangles to say that the radius was equal to the height. Because if we couldn't figure out that relation, we wouldn't be able to get this in terms of 2 variables. So it can be a lot harder if it's 3 variables. We want to try and use some tricks that we have. And eventually we needed to know what dV by dt was. If it was 9, a nice number, we could just get 1/4 pi. Okay, as a 10-meter long ladder rests against a flat wall, its bottom slides across the ground at a constant rate of 50 centimeters per minute. After 2 minutes, how fast is the height decreasing? So what we have here is the ladder is in a room, or maybe it's outside, someone's working on it, right? And the ladder is resting on this kind of wall here, right? So this is your ladder. Okay, and we know that the ladder is 10 meters long, so I'll just write 10. We don't need to write 10 meters, I just like to write the number. Helps me visualize it a bit more. And it slides across the ground, the bottom slides across the ground at 50 centimeters per minute. So if this is the bottom of the ladder here, it slides across the ground at 50 centimeters per minute. So maybe I will write meters actually. So this is 50 centimeters per minute, and this is what I was talking about before. See how this is in meters and this is in centimeters? We have to get them both in the same units. So I'm going to, since 50 and 10 are decently big numbers, let's make 50 0.5 meters per minute. Right, because 50 centimeters is really just half a meter. So 0.5 meters per minute. Instead of writing 100 or 1,000 centimeters for the ladder, that wouldn't really make much sense. So after 2 minutes, how fast is the height of the ladder decreasing? Okay, so what we can do for this one, let's just see. So the height of a ladder. Well, we know using Pythagoras' theorem that the length of the ladder, we can call it, well, let's call the height h. Okay, let's call this length from the ladder to the wall L. And we don't really need a variable for this, honestly, because the hypotenuse is just going to be 10. So we can say 10 squared equals the height squared plus the length squared. So the length from the wall of the ladder squared plus the height of the ladder vertically is equal to the hypotenuse of the ladder squared. So if we were to differentiate the left and the right side here, 10 squared is a constant, so the derivative of that is just 0. This is going to be 2h dh dt, and this is going to be plus 2l dl dt. Okay. So now what we're going to do is, now that we know that one side's equal to 0, we can just start plugging in values. So 0 equals 2. The height of the ladder, let's see here. Meters long. Let's see, how could we solve this? Oh, okay. So this is a bit of a trickier one. We're not innately given specific values right away. So they say that it's going to the right at 0.5 meters per minute. And then it's also asking us after 2 minutes how fast is the height of the ladder decreasing. So if it's moving to the right at 0.5 meters a minute, after 2 minutes, that's going to be 0.5 meters a minute, just unit conversions, times 2 minutes. So the minutes will cancel, and this will be 1 meter. So after 2 minutes, it'll have moved to the right 1 meter. So that's going to be our L. So instead of L, I'll just put 1. And then we can use Pythagoras' theorem here because we know that 1 squared plus h squared will equal 10 squared. Okay, so if we move this 1 squared over, h squared is going to be 10 squared minus 1 squared. So this will be 100 minus 1. Okay, 100 minus 1. So 100 minus 1 is 99. So h is going to be the square root of 99. Okay. So now that we know that the height is the square root of 99, let me just kind of write that sideways here. So now we know h is 99. Okay. I'm just going to kind of clean this up. So 0 equals 2h, so 2h is root 99. dh dt, how high or how fast is the height of the ladder decreasing? That's what we're finding, so dh dt is the same. Plus 2, the length is 1, so I'll just write 2 times 1, so that's just going to be 2, times dl dt, which is 0.5, so that's just half of 2, so this is plus 1. So negative 1 equals 2 root 99 dh by dt. So the exact answer for dh dt, it's going to be a negative value because the height's decreasing as it moves to the right, as the bottom moves to the right, right? We're going down in height. It's going to be negative 1 over 2 root 99. We could rationalize this or do whatever we wanted, but our units for this will be centimeters per minute. All right, so I'll just write centimeters per minute. Okay, so that's going to be your answer there. So 2 friends are testing which type of balloon will float faster, hydrogen and helium. Darlene's testing the helium balloon, while Jeremy's 70 feet away watching how fast the balloon floats. Okay, so let's just draw this out here. So if this is Jeremy over here, the distance from to him and Darlene is 70 feet. Okay, so Darlene's here. I'm not going to draw Darlene just for the sake of simplicity. When the balloon's elevation is 45 degrees, so the balloon's right here. This is the helium balloon, right? Darlene is releasing the balloon. The elevation angle's 45 degrees. So if Jeremy's looking straight at the balloon, this angle's 45 degrees. The angle's increasing at a rate of 0.91 radians per minute. Okay, so now immediately I see that this is degrees and this is radians. That's a bit of a problem. So we have to get either radians to degrees or degrees to radians. Whenever we're differentiating or using calculus, we always want it in terms of radians, because degrees isn't like the SI unit. We always want it like as a unit that we can use like in terms of graphing and stuff. It's going to be a lot easier. So let's do radians. 45 degrees is pi over 4 radians, just from the unit circle. So this is pi over 4. And the increasing rate is 0.91 radians per minute, so that's going to be d theta by dt if we were to write a variable for it. Okay, so let's call this height, here. Let's call this height here x. So we know the angle, we know the distance from Jeremy to Darlene to be 70, and we know the height is x, so we can write tan theta is going to be x over 70. It's going to be x over 70. So if we were to take the derivative of everything, right, theta is considered to be our inside for this question, just like for sine of 2x, 2x is the inside. So the derivative of tan is secant squared, so secant squared theta. And remember, we have to multiply by d theta by dt because that's our inside. We have to use the chain rule for this one. Okay, so before we get into like the main part of it, let's just read the rest of the question. Meanwhile, when Jeremy releases his helium balloon, this should say hydrogen because they can't release the same one, and Darlene observes the same distance, the balloon rises at a rate of 1.4 radians when the balloon's angle of elevation is 30 degrees. So, assuming that Jeremy's is hydrogen and not helium, does the hydrogen or helium float faster in this case? So we're trying to figure out, I'm just going to actually fix this right here. This should say hydrogen. Okay, so if this was hydrogen, does the hydrogen or helium float faster in this case? So we're trying to figure out the rate of change at which this x is changing. And whichever one has a greater value, that's going to be the one that floats faster because it's going to kind of push up in the air quicker. Okay, so back to this here, secant squared theta d theta, that's just going to equal, if we use our quotient rule for differentiation, it's going to be dx by dt times 70, right, over 70 squared, yes. Because remember, our product rule, we're always dividing by that bottom number square. For our quotient rule, we're always dividing by that second number squared, that bottom number squared. So secant squared theta, that's just 1 over cos theta squared. So 1 over cosine of pi over 4 squared times d theta by dt for Darlene. That was 0.91 radians. Okay, dx by dt, that's what we're trying to find. Okay, and this can simplify, the 70 and the 70 squared. Those will cancel, so it'll be dx by dt divided by 70. So we're just going to take 1 over cosine pi over 4. Okay, so cosine pi over 4, remember that's going to be root 2 over 2. So if we're squaring that, that's going to be 2 over 4, right? Because it'll be root 2 squared is just 2 over 2 squared, which is 4, which is a half. And then we're taking 1 over that. So 1 over 2, that's just 2 times 0.91. And then actually, let's just skip and just multiply by 70 to get rid of this 70. That's going to be the rate at which the balloon is rising. So 2 times 0.91 times 70, that's 127.4. And remember, our units are going to be feet per minute, right? Because that's what the question indicated, so feet per minute. So every minute, this balloon's going to rise at 127.4 feet at the instant that it's 45 degrees for the angle of elevation. So I'm going to erase this and just, actually, let's keep it. Let's keep 127.4 feet per minute. Okay, so this is for Darlene. I'll indicate that here. So now for Jeremy, we're going to use this same idea here. They're still 70 feet away because the question said when Jeremy releases it, Darlene observes at the same distance. It just has a different d theta by dt and a different angle. So remember, it'll be secant squared theta times d theta by dt is going to equal dx by dt times 70 over 70 squared. So we're just going to divide by 70 right away. So secant squared theta, well, remember theta was 30 degrees for the second case. So for the second case, theta was 30 degrees. And 30 degrees is just pi over 6, so this is going to be 1 over cosine of pi over 6 squared times d theta by dt for Jeremy was 1.4 radians. 1.4 radians. This was, and we actually have to multiply by 70 now as well. So I'll just put brackets there instead. This is dx by dt. Now we just multiply all those together. So 1 divided by the cosine of pi over 6. Okay. That's going to be 1.15, and we're squaring that. So 1.33 times 1.4 times 70. That's going to be 130.1. So dx by dt for Jeremy is 130.7, and this is going to be feet per minute. So this is his balloon, the hydrogen balloon's rate of the rate at which it pushes up into the air in feet per minute, and this is Darlene. So if we compare these, Jeremy's is about 3.3 feet per minute faster at that point. So at these exact instances, at these exact moments, Jeremy's is going to be rising faster. Okay, so this can't be generalized to every elevation, right? Because hydrogen might float slower at a higher elevation, but when this angle of elevation is 30 degrees, this angle of elevation is pi over 4 radians, or 45 degrees, Jeremy's is going to be floating higher. Okay, so that's how we can use related rates to solve these problems. We just went through 4 or 5 here. I hope they made sense. And like I said, this is probably my favorite unit just because we're using like the chain rule, we're using derivatives, sometimes we're using integration, like to figure out formulas for volumes and stuff like that. So I hope this made sense, and I'll talk more about these kinds of problems in some future videos. So I'll see you soon, and thanks for watching.